the idea behind the Coriolis force. Okay. Now, المسألة مسألة اختلاف وجهات نظر. How? Say, for example, you are in, say, for example, you are in an airplane or in a car, and the car starts turning. You end up going against the door. Okay, what is this force that is pushing you towards the door? Now, depending on whom you are asking, depending on whom are you asking, okay, there is no screen to share at the moment. I'm just talking, okay? Depending on whom you are asking, you will get two very, very different replies. Okay. Say, for example, when you're in a car and someone is accelerating the car, you feel that you're being pushed backwards. Okay. Now, what you would say, or what I would say, is we are being pushed back. Yet, from a physics point of view, a physicist would tell you, no, you're not going backwards. You are not moving. The car is pushing, the seat is pushing you forward. So which is it? Am I going backwards, or is the car going forward, or is the seat pushing me forward? Again, say in the car. Let's stay in the car, not go anywhere else. We're driving, we're going to the side, I end up moving. Now, what I would say is, I am moving towards the door. Yet, what a physicist would say, okay, is that I am not moving, but the car is moving towards me. Okay.
دكتور سمع
ايوه
بس الشاشة ما مشاركينها معنا ما نشوف شيء.
ما في شاشة حاليا، انا بس جالس اتكلم.
تمام.
طيب بشاركها بعد شوي، لما في شاشة بشاركها بعد شوي. طيب حاليا ما في شاشة. زين. So the question is, which one of us is correct? Am I moving, or is the car moving? Now I'm going to present. Here we go. Now, when this car is moving, which one is correct? Is the person moving towards the door, or is the door moving towards the person? What actually is happening is what we call a difference of opinion in English, or بالعربي اختلاف وجهات نظر, okay, is that we are looking at these things using two different frames of reference. Remember in chapter 4 when we spoke about frames of reference, your speed versus with respect to one reference frame, and then your speed with reference to another reference frame. Okay, so we can reconcile these two by saying, let us choose a frame of reference. Now, usually what happens is when we are in the car, we use our car as a frame of reference. So in our head, the car is not moving. Okay, I am moving. That makes sense. Yet what the physicist might say is, no, that's wrong. The Earth is moving. Okay, and if the Earth is not moving with respect to you, because we're all moving with Earth, and thus we should be using Earth as our frame of reference. Now, we have an issue. If we take Earth as the frame of reference, okay, our forces are actually the totally opposite. Okay. And we have already experienced this one time as a difference of opinion, but we did not name it. So today we're going to give it a name. See, this car is turning because look, these tires are going at an angle, so it is turning. Let me bring up the chat screen here, so if anyone is asking or writing anything, I can see it. This is still chapter 6. Yeah, this is the last thing remaining from chapter 6. Okay. All right. Now I can see your messages in real time. Okay. Now, remember when we spoke about inertial frame of reference and non-inertial frame of reference. Okay. What we said at the time was an inertial frame of reference, Newton's laws are okay. They work. Non-inertial frame of reference, Newton's laws don't work. That's all we said at the time. Now, what happens is while your car is accelerating, it is a non-inertial frame of reference. There's an extra acceleration. Your frame of reference is being accelerated to the side. Okay, the force that we as a passenger feel in terms of physics is what we call an inertial force. There is no physical origin. Okay, so there is no tension or friction or gravity or a push or a pull that is causing this force. It is simply because your frame of reference, your car is moving, is accelerating, that you feel this force. And one very, very famous example of this is something that many, many people get mistaken. We have the centripetal force, which if something is going in a circle, it's going towards the center. Yes? Which is what we spoke about yesterday. And then you hear many, many people speaking about a centrifugal force, which they say, if we have a circle, a centripetal force is a real force. It is caused by the tension in the spring, or by the gravity, or by the tension in the spring or string or something like that. Okay, there's an actual physical reason for it. Okay, so this is an actual force. Centrifugal force is what we call an inertial force. It is not real because there's no reason for it to happen. Yeah, there is no tension, no gravity, no spring. It's only there because there is movement. Okay, so if you want to reconcile the 2 points of view, okay, we add centrifugal force to make the net F equals 0. Okay, it's only an imaginary force. Okay. Now, your book gives you like 3 or 4 different examples, but the idea is the same. And they use the term Coriolis force for what we call centrifugal force. Okay. I'll do example number 9 since we're still in chapter 6, and then I'll move on to chapter 7. Okay, example number 9. Motion of a projectile fired vertically. This is a rather nice problem, actually. And it involves a bit of calculus. Where's 6.9? Is this 6.10? Ah, here we go. A 10-kilogram mortar shell is fired vertically upward from the ground with an initial velocity of 15 meters per second. Okay, this is nice. Initially, it goes up at 15 meters per second. Determine the maximum height it will travel if atmospheric resistance is measured at 0.01 v squared newtons, where v is the speed at any instant. Now, the new thing in this problem, which we haven't done before, and which is actually very realistic, is this v squared bit. It means that the resistance, I actually told you this yesterday, that in realistic situations, this is it. The air resistance is proportional to the square of the velocity, which means that the faster the projectile goes, the more resistance it experiences. And the slower it goes, the less resistance it experiences. So the question is, usually we say, okay, F equals MA, V initial, V final. And usually what we say is sum of F equals MA. Okay. So there are no forces going up, but there are 2 forces coming down, mg, gravity, and against the direction of motion, so downwards, is drag. So usually what we would say is mg plus the force, the drag force, equals ma. But here we have a problem. Which FD? Since there is a negative acceleration, the velocity starting at 50 meters per second is going to be less and less every second, every moment, which means FD is going to change every moment. So how do I calculate this FD? How am I able to do this equation if my FD changes in every second? There's no point. Is there even a point in me trying to do it? Okay. And the answer is we cannot do this using our normal static equations. We need to account for velocity. Okay. So what we do is we use a bit of trickery. Okay. Let's first write what our parameters are. Okay, what our knowns are and unknowns are. So my initial position is 0. So I will take this to be 0 in the y-axis. Okay. My final position, I do not know. This is what I actually need to find out. My initial velocity is 50 meters per second. My final velocity will be 0 meters per second. Okay. My gravity force is equal to mg. My drag force is equal to 0.01 v squared. Okay, which is what's causing us all the grief. Okay, and that is what we have. That's all the information that we have. Okay.
Doctor,
now
can you
what
repeat
is
about what is meant of v squared?
v squared is the velocity. So literally speaking, when the velocity is 50 meters per second, your FD is 0.0150 squared. So I'll do 50 squared times 0.01. So my FD will be 25 newtons. Okay. When my velocity is 40, my 0.01 times 40 squared is going to be 16 newtons. When it's 10, okay, it's going to be 1 newton, and so on and so forth. Okay, so my force is literally dependent on the velocity. Usually we simply say force is 10 newtons. Here we're not saying that. We're saying it actually changes every single second. Okay, every time we have one of those, every time our velocity changes, my force changes. Okay, so because it changes at every time, we will have to use integration. There is no other way. Now we know that the sum of forces is equal to ma. This equation of Newton is still true. Okay, now just 1 second. Okay, so I'm not going to write it the same way as your book. Okay, so I'm going to write it what I believe to be is the easier way. Your book loves to use minus signs. I hate minus signs. Okay, so I'm going to be taking down as positive. Your book is taking down as negative. So FD plus mg is equal to ma. My FD is 0.01 v squared plus mg equals ma. So see, I started from the same rule, and then I am simply substituting in it. Okay, so far so good. Okay, is there something I'm missing? Ah, yes, 10 kilograms mortar shell. So I have my mass equals 10 kg. So let me put in the numbers. 0.01 v squared plus 10 times 9.8 is equal to 10 a. I'm using 9.8 now to be able to do it quickly. Yes.
Should be 8.1 Newton gravity.
Yeah, I'm using 8. very quickly. Let me do it 9.81 just to be absolutely accurate. Okay, 9.81. So this will be 0.01 v squared plus 98.1 equals 10a. So far, so good. Do we agree with this so far? Okay. I'll put them all onto one side. Okay. 0.01 v squared plus 98.1 minus 10a equals 0. Now, I don't like the fact that I have 10 and 98 and I'm going to try to make it look simpler. You might agree with me, you might not agree with me. I will divide everything by 10. So I'll have 0.001 v squared plus 9.81 plus a equals 0. Now we want to know what is a. Okay. We want to know what is a. Sorry, minus a.
Doctor.
Yeah, minus a. Okay. Yeah. Someone is saying something? Yeah. Okay. Now we want to find a. All right. There is no easy way to find a. The only way to find a is to take into consideration since this f changes every second, I have to integrate it over every single time possible. So I'll say a is equal to 0.001 v squared plus 9.81. Since acceleration depends on velocity, now if you have not done calculus 1 now, this might be a headache for you. Since my acceleration depends on velocity, it's actually a function of velocity. Okay, so we end up with acceleration as a function of a position every single point will be equal to the change in velocity at every single change in position. So our equation ends up looking like this. V dv equals 0.001 v squared plus 9.8, and I'm only dealing in the y-axis. Okay. Now we separate the variables. We bring all the v's to one side. Where did we change the sign?
دكتور
أيوة.
أعتقد من البداية المفروض كنا نسوي اف دي minus mg.
No, FD and MG are in the same direction. Why would one be positive, one be negative? Either both are minus, either both are positive. Because they're in the same direction. Your book takes it minus. I took it positive because why should I give myself the headache of minus signs? We're only dealing in one direction, not other directions, yeah? So I chose down to be. So your book says this is minus and this is plus. I am saying this is plus, this is minus. Okay. Why did I divided by 10? Here. I divided everything by 10. Okay. Now finally, we can do the integration, which is a real pain. V dV over 0.001 v squared plus 9.81 integrated. My initial velocity is 50 meters per second. My final velocity is 0 meters per second. And I will integrate here dy, which is going to be from 0 to whatever maximum height we have.
دكتور I solve this problem طلع لي في الناتج 5 في 10 أس 2 لكن في الكتاب 5 في 10 أس 3 إذا تعوض 5 في 10 أس 3 ما يطلع لك 112 أو 118 كذا حاجة بيطلع لك رقم كبير لكن لما تعوض 5
احتمال
يعني لما تسوي الكالكوليشن الأخير ما يطلع لك الهايت نفسه فحليت المسألة فطلع لي 5 في 10 أس 2 ما هو أس 3 إذا ممكن تتأكد منه.
خلينا نشوف. هذه بتصير فقط اتش اللي هي الهايت، صحيح؟ Okay, I'll rewrite the entire thing because I don't want to skip steps. 50 to 0. V over 0.001 v squared. I'll just divide the whole thing by, I'll take v off the top. I will get dv divided by 0.001 v plus 9.81 divided by v. Okay. And I'm going to cheat. Because we're running late and I want to go to chapter 7. This problem turned out to be really long.
لأن الإشكالية هنا في أظن هو قسم بعد على 10 فأعطاك 0.0001 يعني 0.331 في تربيع فلما تجي تشتقها الفي تربيع ضربها في 2 له بيعط هو سواها يعني باور 3 فهو المفروض ما يسويها باور 3 لأن عندنا احنا 0.001 في تربيع ما عندنا 0.3 أصفار معها فلما تجي تشتقها تعطيك مسمى يعني 1 على 2 من 100 2 من 1000 صح.
You're correct.
فما أعرف والله إذا أنا غلط أو الكتاب غلط لأن حليت أكثر من مرة.
No, you're correct. Okay. You are absolutely correct. Okay. And it needs integral by parts, which is a pain. So we'll just believe the book, okay, in saying that this is equal. Actually, I think 5 times 10 to the 3 is 5,000. No, the book has made a mistake. It should be 5 times 10 to the 2. So it should be 5 times 10 to the 2 ln of 0.001 v squared plus 9.81 over the limits 50 to 0, which will give us a final answer of 113.5 meters. Okay, the book has made a mistake. This book has quite a few mistakes, doesn't it? Okay, I'll do something. I'll solve it in absolute detail and I'll send it to you. I'll upload it over Moodle. Okay, because it needs a lot of calculus. Okay, so I'll solve it and I'll send it to you. If there are any questions that require calculus in a quiz or in a test, it will not be something as complicated as this. Okay, it will be something very, very easy to do the integration of. Something like, you know, x squared becomes x cubed over 3, or 1 over x is ln x. That's it. Okay, we will not bring in something that requires integration by parts or integration by substitution. Okay, I know many of you have not done Calc 1 yet, and some of you are doing it at the moment. And although most of you have done this in high school, you have probably forgotten this. Okay, so I'll solve this step by step, and I will upload it for you. For now, let's go and do something a tiny bit more interesting, okay, and less headachy. Okay, and that is kinetic energy and work. Okay, so energy is a word that we use quite often in day-to-day life. Okay. How do we define it? What is energy? In physics, energy is a scalar quantity assigned to an object or a system of objects, meaning it's not a vector. Yay, no directions. And it can be changed from one form to another, but it cannot be created or destroyed. Details will come in a bit. Okay, but someone was saying that this is calculus, not physics. Mathematics is integral to pretty much any field of science. So whether you're doing physics, chemistry, biology, computer science, sometimes mathematics and calculus are going to show up. And in physics, actually physics and mathematics are very, very intertwined. Okay, the higher up you go in physics, the more mathematics-y it becomes. Actually, in high-level physics, when you go to things like quantum theory and general relativity, things stop making sense in a physical sense. They just start making sense in a mathematical sense. Okay, it's an unfortunate thing that not everything can be thought of physically, but only mathematically. لكن تبارك الله أحسن الخالقين. All right. So I'm going to actually switch. I'm going to start with kinetic energy, and then I am going to come back to work. Okay, so I'm going to start with 7.2, then come to 7.1. What is kinetic energy? Kinetic energy is the energy of motion. If something is moving, it has kinetic energy. So far, so good. It moves, it has energy. For an object with a velocity which is very, very much less than the speed of light, okay, you know what the speed of light is? 3 times 10 to the power 8 meters per second. The translational kinetic energy, now there are a few new words here which I'm going to underline, is defined as half mv squared. What does this mean? Kinetic energy is the energy that has to do with movement. It is equal to half mv squared, but this only works if we are well below 3 times 10 to the power 8, so pretty much everything we do in this course. And this is to do with translation. So an object going, let's use a car as an example. An object going from one place to the other, okay, with a velocity that is like this. Okay. What is the unit of kinetic energy, or any energy actually? Joule. Okay, you might have seen it if you're looking at your boxes of juice or cans of Coke. It will always give you something in calories and something in joules. Okay, 1 joule is equal to 1 kilogram meter squared per second squared. Just opening your and I will also define it using a different way. If you remember in chapter 4, when we spoke about chapter 5, when we spoke about Newton's second law, we said that F equals ma and F equals dp over dt, right? Change of momentum. Here also, we can write it as k equals half mv squared, and also as k equals p squared over 2m, where p is momentum. Again, momentum actually comes later, but just bear in mind that momentum can be related to kinetic energy, and momentum can be related to forces. Okay. Let's take a look. You have all written this down, k equals half mv squared? Good. Which is moving faster? A car and a truck have the same kinetic energy. Which one has a larger speed? The car, because it has a smaller mass. The truck, because its large mass makes the kinetic energy very large. Both have the same speed because their kinetic energies are the same. Or D, I have no idea. Remember, k equals half mv squared or p squared over 2m. Excellent. Everyone has chosen the correct answer, which is A, because indeed it does depend on mass. All right, good. And one more question. I'll put it on a whiteboard. Say, for example, okay, say, for example, we have a train. Okay, say, for example, we have a train. And there's a person inside the train. Let's use the same example we used a couple of chapters ago. And this person is moving at 1.5 meters per second inside the train, while the train itself is moving at 15 meters per second. What is the person's kinetic energy okay, relative to the moving train? Can anyone do this calculation?
Repeat, Doctor.
So we have a train that's moving at 15 meters per second, and a person inside the train. So while the train is moving at 15 meters per second, we have someone inside walking at 1.5 meters per second. What is the kinetic energy of the person relative to the train and relative to the ground? So if we take the fixed frame of reference to be the train, then my person is only walking at 1.5 meters per second, correct? So my kinetic energy of person inside the train will be equal to half. I'll give the person a mass of 75 kgs. So half m v squared, which is equal to 84.4 joules. Okay, there's no direction, it's a scalar, so just 84.4 joules. That's how much energy content this person has because of his movement. However, what if I want the kinetic energy of the person with reference to the ground? What is it going to be then?
Doctor, we first find the velocity of person relative to ground.
Perfect. Excellent. So it will be 15 plus 1.5.
50 plus 1.50. 15.
Yep. And this will give us about 6,830 joules, give or take. Yes?
Yes.
Okay. So this is the same person, but we got two very different energy contents because we're taking two different frames of reference. Okay. I'll do one more question. What is the kinetic energy of the person with in a frame which is moving with the person? So if there is a camera on the person, okay, we get a camera, we attach it to the person like this, okay, and we say, what is it, the person's kinetic energy? Excellent. Perfect. It will be simply 0 joules, because if the frame of reference is moving with the person, then the relative velocity is simply 0. Okay, so you will not be measuring any velocity, which means V is 0, so your kinetic energy is 0. Excellent.
Doctor, I have a question here. The kinetic energy of a person among the ground, I got in the calculator, it is 1,000, 1 0. It's different answer than what you get. I don't know why. I got 10209.3055.
Did the calculation in my head, so I might have made a mistake. Did I make a mistake somewhere? Yes. What did you get?
10209.37.5. Yeah.
So I'd say about 10.2 kilojoules. Thank you. I make mistakes often, so it's always good to keep up with me, make sure that what I'm doing is correct, and I'm not messing up the calculations, because as you can see, I do mess up calculations quite often. Okay, I'm very gaffe prone. Thank you for that.
Welcome.
Going back. What? I have no idea what.
Doctor, can you
Okay.
repeat why it's 0?
So we do half mv squared, right? We consider the kinetic energy to be equal to half mv squared. Now, if we are measuring the velocity with reference to the train, then the velocity is 1.5. So we do v equals 1.5. If we are measuring the velocity with reference to the ground, it is 1.5 plus 15, so 16.5. If we are measuring the velocity with reference to the person himself or herself, what is the velocity then? It will simply be 0. Yeah. ايش سرعتي بالمقارنة مع نفسي؟ 0. I don't have a velocity with respect to myself. So my kinetic energy with respect to myself is 0. Yeah? Okay. Let's take a very quick revision of chapter 2, scalar products. A dot B is equal to AB cosine theta. B cosine theta will give me the x, this, and A cosine theta will give me this. Okay. We will define, okay, a new thing now called work. Okay. And here, I will call this 7.1 because in your book this is 0.1, and in your book this is 7.2. Okay. Let's consider a block which is being pulled by a force F. Okay. Now this force F, okay, does it really affect the motion of the block in both axes? Yes or no? So you have F cosine theta and you have F sine theta. Now, as far as I am concerned, I am only interested in moving the block from here to here. So can we say that the F sine theta component is wasted? Can we say this? Yes, no, maybe? Good. Okay. All right. So in physics, work is done on an object when energy, okay, so we've spoken about energy, right? When energy is transferred to the object, we say work is being done on the object. Okay. When energy is taken away from the object, we are saying energy is work is done by the object. But point is, work is related to energy movement. Okay, if energy goes in or energy goes out of an object, we call it work. Okay. Another definition we can give work in physics is when a force acts on something and it causes it to move. It causes a displacement, not movement, displacement from one position to another. Okay, it is doing work. So, how do we write this in physics? Before physics, let me give you an anecdote. You're at home, your mom comes to you and says, do this. Okay, I'll do that. You spend half the day doing the thing that your mom told you to do, only at the end of the day to find that your mom is unhappy with what you did at home because it's not in the way she wanted it to be done. Okay? I don't know about you, but this is very normal for me. Okay? You spend half the day working, doing something, and at the end of the day, you're like, كأنك ما سويت شيء, يا ريتك ما سويت. Okay? This is something very common in Oman. Yeah? Moms want things done to be in a very, very specific way. If you do, it doesn't matter if you did the thing. If you didn't do it in the way that she wanted it to be done, she's not happy. Turns out, physics is exactly the same way. Okay? So it turns out in physics, we define work as a force that acts work that acts on some work is a force that acts on something in the direction of causing displacement. Okay, so if you want to go from point A to point B, which is what your mom wants you to do, okay, and your mom wants you to do it this way, A to B, or in this case, physics wants you to do it this way, A to B, okay, and you decide, you know what, أنا بصير أشتري شيء من الدكان, but on the way, I'm gonna go شوية بيت صديقي, بمر, بسوي أشياء, وبعدين برجع. So you decide to do it this way. You did the work, right? You did the job. You went from point A to point B. You took a very long route, but you went from A to B. But physics will only credit you, okay, for this distance, for the displacement, not the distance. Remember, chapter 2, chapter 3, displacement and distance. Physics is only concerned with displacement when it comes to work. Okay, so it doesn't matter, okay, if you took this thing that weighs 10 kilos and went all the way around to go to point B, it will only credit you for point B. That's it, nothing else. Okay, so let's define it in terms of mathematics now. Okay, I hope this example of mothers, Allah yahfadhum lakum jami'an inshallah, will stick with you in your head. Okay, let's define it mathematically. For an angle theta between force and displacement, okay, work is defined as F dot D. the dot product, otherwise known as FD cosine theta. It doesn't matter if the force is at an angle, it will only give you credit. You have only done work in that direction, in the direction of displacement, not in any direction whatsoever. Okay, F dot D, FD sine theta, FD cosine theta. What if our force is like that drag force in problem 6.9? It changes. How do we do it then? Well, we have the definition of work to be equal F dot D. In that case, what we say is work, okay, on AB will be equal to the integral of F dot D in the straight direction over the path. Okay, we will of course do examples to make this clearer and clearer, but what does this mean? Okay, it means that if I'm taking this path from A to B, okay, I'll rewrite it here. No, it will only be with cosine ma'ad because it is defined as the dot product. Okay, so say for example, okay, we have this. At any given point, I will take this point. I have a force that is going like this. Okay, this is my direction of motion, dr, okay, along the path. This is my angle theta. The component that is actually doing the work is F dr cosine theta. Okay, R is the direction, Asma. Okay, so instead of saying X, Y, Z, I'm saying R at the moment because I don't know what exactly is it. Okay, also it could be a combination of X and Y. So then it will be a double integral, for example, or a path integral. So for the moment, I'm making very, very general and saying it is R. Okay. So we have two equations. Constant force is very easy, F dot D or FD cosine theta. Non-constant force is given by an integral. Okay. Let's take these two examples. This person, is it the indefinite integral? No, this is a definite integral. It has to be along the path. See here, I've written the path. So it is a definite integral. It has to be from place A to place B. Okay. All right, let's take two examples. This person on the left is taking about 50 kilos, and once moved up, he's standing like this. How much work is this person doing? Tasneem, yes. The integral is the general form. The constant one, FD cosine theta, is a special case of the integral. Okay, so the integral will always work. The FD cosine theta, the fixed form, will only work for fixed forces. Okay, so this guy is holding something up. He has been holding it up for an hour. Okay, how much work is he doing? Yes, 0. Okay. Okay, 0. All right. Integral, Adnan, is most useful. You can do it for both, but it's most useful if the force changes. There's no distance here. Okay, so 0 force. What about this person? He's pushing this car. He's pushing it in the direction he wants it to push it. Okay, but there is no movement, as you can see from his force, from his face. So again, 0. Okay, it's the sad case. It doesn't matter how hard you're trying. If mama's not happy with what you're doing, you haven't done it. You haven't done the work. And this is exactly the same with physics. It doesn't matter how much these people are pushing or holding. Okay, since they are not moving, it is 0 work done. Okay, what about total work? How do I find total work? I have 3 people pushing one very big box. What is my total work? Well, my first person will be F1 pushing with force 1, my second person F2, my third person will F3. Each one will have a work. And since they are scalars, work is a scalar, it's not a vector, I simply add them all up. And this, before we even go into much more details, gives me personally the first reason why I prefer to work with work rather than work with forces. Although forces, we are used to working with them since school, and work is a new thing, but work is very, very nice because it's a scalar. It's not a problem if I'm going forward or backward. It's still a scalar. I just add up all the numbers, and the adding is easy. 1 + 1 + 1. Normal addition. I don't have to worry about directions or different axes. It's just numbers. I'm just adding them. Simple. Good. Okay. What about dependence of angle? Okay. Again, FD cosine theta. I've used a different letter here, S, so that you get a feel that the letter doesn't really matter. Okay. When theta is between 0 and 90 degrees, our work is FD cosine theta. What about when theta is equal to 0? What is our work? Excellent. Maximum. It's just FD or FS because cosine 0 is 1. So our maximum force, also our maximum usefulness, okay, is when we are exerting the force only in the direction of motion and no other direction. Okay, so this is the exact way physics wants us to do forces, only in the direction of displacement. This is the exact way what our moms want us to do work. Okay, when theta is equal to 90 degrees, what's cosine 90? Zero. So when you're moving the block this way, although gravity is pulling it downwards and there's a normal force, the work done by gravity and by the normal force is 0 because they are at 90 degrees to the displacement, to the direction of displacement. Okay. Here's a person picking up a box and running. Okay, and this person is running in this direction. What is the work done by gravity? Anyone? FS 0 mg 0 0 0 FD FS. Okay. Gravity is downward, right? This person has already picked it up and is moving in this direction at 90 degrees. So the angle between them is 90. Gravity is working downwards. This person is working that way. So if you ask physics how much work this person is doing by gravity against gravity, the answer is going to be 0. he's not working against gravity anymore. He worked against gravity at the beginning when he picked the box up. After that, he's not working against gravity. Now he's working against air resistance. He's working against other things. He's not working against gravity. He already done that before. Okay. Whether he's holding just the box at rest or if he's moving with constant velocity at the same level, it's going to be 0. What about when our angle is 180 degrees? So my thing is moving in this direction, but my force is in that direction. Something like friction. Excellent. It's going to be minus Fs. And that is negative force. Negative work, which means we said also another definition of work is transfer of energy. So if I am doing minus work, I am taking the energy away from the object, meaning eventually the energy of the object is going to reach 0. And also we have already said that kinetic energy equals half mv squared. So when my energy becomes 0, what is my velocity? Also 0. Okay, so now you're seeing we are starting to put everything we have been learning so far together. Okay, it's like pieces of the puzzle are starting to fit together. You have force in one direction, the force in the other direction causes work against the object. It reduces the energy content of the object. It's taking energy away from the object. When your energy runs out, your velocity becomes 0. Okay, so your force is taking away the energy by doing work, which is making it stop. This is why we have acceleration. We're taking away energy. Okay, many times the work done by the friction force is negative. Okay, I want it's how much work do we have? Okay, it's 122. So I am going to stop here, and on Monday, inshallah, I am going to finish off these few examples, which are actually very, very quick. And then I will move on to the work energy theorem, and then later on, power. Okay. Yes.
Is K equal W?
K equals kinetic energy is sometimes no. Sometimes it will be equal, sometimes it will not be equal. Okay, let me stop the recording.